move on to, those are all the base things. And we have discussed about the risk and CISC architecture. And I told you nowadays the insist is much on risk architecture. That is the reduced instruction set computer. Two things. One is the number of instruction class is reduced, and almost all the instructions are of same size. So just keep remember that is very very important. Okay. The instruction size, what I meant is that if it is a 32-bit instruction, the instruction is 32-bit. Okay, but when you just go with the CISC-based machines, the size may vary from 1 to 6 bytes, or nowadays like even 18 bytes. When you go with the advanced processors, even it may vary still 18 bytes, but this is not in case of RISC-based machines. And the most important thing is load store architecture. So hope I said what is load store architecture. So whatever the ALU operation that is going to be performed by the processor, the operand of those instructions should be in registers. Okay, say for example, while adding or subtractions or whatever it is, it should be in registers. So since the data should be in registers, what has to be done? It has to be loaded from the memory first, and then the operation has to be done and then stored back to the memory. So that's why RISC-based architectures are load store architecture. Keep remember this word. So I told you, like though we are, I mean, the last semester you read about ARM architecture. Here, this in our textbooks, whatever the examples they have given is focused on MIPS 64 architecture. Again, it's a kind of RISC-based processor. Okay, so MIPS, MIPS-based architecture in our syllabus we have. So and then right, we move on to our content. Current right, we are looking to what are the various classes of computers, like 5 categories: PMD, desktop servers, clusters, and embedded computers. And then right, we move on to this is very important, the parallelisms. Okay. So normally when you just go with the applications, two kind of parallelisms that can be done. One is the data level parallelisms, another one is the task level parallelisms. So at application side, only these two things can be done. So there should be some hardware architecture which should support these two things. One is data level parallelism, another one is task level parallelism. So since classification on parallel architectures, so they just generally classified into 4 categories as SIMD, SISD, SIMD, MISD, MIMD. So I told you. So this also keep remember. SISD is for DLP. SIMD is for again DLP. MIMD is for TLP, task level parallelism. Only MIMD is for task level parallelisms. We don't have MISD. So first SISD and SIMD will be for data level parallelisms. So maybe right based on this you may get a question. I mean, suppose if that is a 2 mark, so you may get a question on this. Okay. So this part right we have discussed in the last class. So today again right we will go for some more things. Current right we will try to define what is exactly the computer architecture is. Okay. Just share the PPT. Okay, is it visible?
Yes, ma'am.
Yeah. Okay. So today, right, just we will go for the defining the computer architecture. This is the next topic. So when you talk as computer architecture, mostly, right, they are focusing much with instruction set. So every computer first thing architecture, the first thing that the people, the designer mind is it is all about the instruction set. That is the very important thing. Other than that, a few more things has also be considered. So we will see all those things. So that's it. The most thing is right. They have to this one. They need to determine the attributes. That is very important. Rather than maximizing this performance or energy, because that might be the goal. So whenever right, you are taking any computer architecture, probably right, we will go for the throughput or energy or something. We will go for that. Beyond that, first we need to determine the attributes that are important for any computers, At the same time, we have to stay with what? Cost, power, and availability constraints. So that is very important. Cost, because it should be a cost effective. At the same time, the power consumption should be less, and the availability. Availability is what we know, right? So whatever the component we are trying to serve, it should be available in maximum. Then only, right, we can able to design it. So those things has to be there. So the first task
Ma'am,
is
your voice is low.
very low.
Yes, ma'am.
One second.
Okay, is it audible now?
Yes, ma'am. It is audible.
One second. Okay, so when you are going for designing, so there are many aspects to be considered. So of that, right, the first one, so these are the four base things that has to get considered. One is the instruction set design. The next one is the functional organization, how it has to get organized. Then the logic design, and finally the implementation part. Okay. So these four are the main aspects when I are going for computer architectures. So of this, right, this instruction set design plays a vital role for computer architecture designing. So this, I mean, in this session, right, we will see like what are all the base things that has to be considered when we are just going for instruction set architectures. In general, right, whenever the major thing is, right, whenever you are going to design any architecture, you should know about the wide range of technologies. That means, right from compiler till operating systems. Because I told you the last class, right, nowadays, right, the growth of this processor has been increasing. It is mainly because of two things. One is the virtual elimination of the virtual elimination of assembly language programming and the vendor independent operating systems. But previous cases and all, right, when we are going to design any processor, what happens is designing a compiler is the mandatory and designing an operating system is the mandatory things. So when you are going to design a compiler, ultimately, right, what we know, we should know about the instruction set. Clear, only if you know the instruction set. Because this what, say, assume in your high level language, if you are writing a code, assume C equal to A plus B. If I'm going to run in ARM based machine, assume the code may be like this. So add AX comma BX. Assume, I mean this what. So if suppose if it is in a Intel based machine, sorry, this is Intel. Okay. This is Intel based machines. When you go for an ARM based machine, it will be like add R0 comma R1 comma R2. So here it will be like this. AX will be it will be like this. But here, right, it will be like this. R0 equal to R1 plus R2. So you know the role of the compiler, right? What it is does, whatever your high languages, it will be converted to your object code. So when it is converting to your object code, what the compiler should know, it clearly knows the instruction set of that specific architecture. So then only, right, you can able to design it. So this was very important. But nowadays, right, I mean, these two things has been completely eliminated. As like when you just go with the Java cases and all, we have a Java compiler. It's giving a bytecode. So that bytecode can be easily converted to a instruction set architecture. I mean, based on instruction set, it can be easily convertible. So that's why they'll say as a platform independent. And most of the things comes nowadays as vendor independent operating systems. But this is the previous case. So when you take the instruction set architecture, it is serves as a boundary between the software and the hardware. This is what it is. Okay, because I mean, you are writing at high level languages, and it has to be executed on the processor. Okay, so I mean, to execute the program, what you are written on high level language to the processor, ultimately, right, it will be converted to the corresponding instruction set. I am just written as a add R0, R1, R2. Okay, but actually, right, when you are just going to convert, it will be as what? 1100, 1100, 1111. So 32-bit size. You got it, Anna? So this is going to be a 32-bit. So the instruction set is going to act as a boundary between the software and the hardware. And the second thing, it defines all the programmable visible components and operation of the computers. So this what? So far, right, we have written a high-level languages. Do you, I mean, does we know that, okay, this are these registers, are we aware of that? Okay, we need to write, I mean, we need to use this register for this case. Have we did like that any so far? Will your high-level language is showing any components relevant to computer architecture? Your program, you have written your high-level language, yes? Is it showing any visible components to you related to computer architecture? Yes
No,
or
ma'am.
no?
No,
No,
ma'am.
right? Yeah, we don't know anything, right? We don't know what is that register. We didn't even know what is that process that we are working on it. Okay, so when you want to know all those things, only with the help of the instruction set architecture, we get to know. Because if you take this instruction, okay, this instruction is add instruction. So this we take 3 registers. All those things only it can be visible with the help of instruction set architectures. And at the same time, right, it is just providing all the information which is needed for someone to write program in machine language. So whatever we need, all the information is provided only by the instruction set architecture. So first, right, just we will go for this one, classes of instruction set architectures. So generally, right, they are going with 2 categories. And nowadays, right, are general purpose register architectures, which means I told you, right, most of the operations will involve the registers. So when you just go with the ARM, you might have come across with ARM2 or 15, right? Okay. In our case, I mean, according to our syllabus, we are going to read about MIPS architecture. So wherein, right, it have 32 registers. R02 or 31 general purpose registers. Okay, and when you're taking the operands, because every instructions will take an operand, and that operand may be either a register or the memory location. So if suppose if I'm having an instruction like this, add r0 comma r1 comma r2, so this is what, this is the operation we are going to perform, and this is the output, sorry, I mean operand. Okay, so this is going to be the operand. So this they say it is opcode. Opcode means operational code. What is that operation? It is going to does. It is going to do addition, and these are all the operands. So these operands may be a register or it may be a memory locations. And I told you general. This is the general thing. When you just go with the instruction set architectures, the operands may be either registers or it may be a memory store architecture. Sorry, yeah, memory locations. Now, right, they are classifying into 2 categories. The load store architectures are RISC, and registers based are CISC architectures. So, which means what is happening is, most of the cases, when you go with the load store architectures, whatever the operation it needs to perform, all those things should be in the registers. That is very important. Okay, so this what, see, both the operands and the destination, for example, addition operation must be in the registers. So these examples. So this is best here. Clear? So when you take the load store architectures, all here they given us PowerPC machine or Spark or RISC-V or ARM or MIPS. Those are all comes under a load store architectures. Wherein, right, it will take the operand in the registers. You people may have a doubt. Keep remember, when they are talking, only they are talking with respect to arithmetic instructions and the logical instructions. Okay, all the ALU instructions. because load store instructions probably right when it is going to load, it has to load it from the memory, and probably um, one of the operand should be a memory operand. Okay, I'm just talking about the arithmetic and logical instructions, wherein those instructions should contain the operand in the register itself. The next one is registers or memory architecture. So in this case, one of the operand for the OR operation may be in the memory while the other is in the register. So for example, add AX, 3000. So what is happening? Whatever the data in AX will be added with the data in the location 3000 and it will be stored in the register AX. So one of the operation is in a register, the other is in memory. You may have a doubt, should it be like this always? It is not the case. Even right here you can have this add AX, BX. You can have a register based also. Got it? So that is also there. But this type of operation is not allowed in RISC based machines, which means one operand should not be in registers. Both the operands should be in registers. This is for arithmetic and logical unit, because you have a load store instructions that should may have a memory operand. Okay, but that is not the case. But in general, right? So when you talk as an instruction set architecture, the operand may be a registers or it may be a memory locations. When you take a RISC machines, most of the operands would be in registers. When you take a RISC machines, maybe in registers or in memory location. And one more thing, let me differentiate. So what is this? What I'm trying to write here? Can anyone say what this instruction says?
Here, both the operands are in memory location.
Okay, so we are trying to add the data in the location 3000 and 4000 and placing the result in 3000, isn't it? But this is completely wrong. Because clearly, right, what is that architecture? It is a registered memory architecture, which means one operand should be in register, the other operand should be in memory. Both the operands should not be in memory. Okay, for any architecture. Please remember, when you just go with any instruction set architectures, only one operand should be in memory. The other operand should be in registers. Okay, this may be allowed. Say, for example, I'm given like this, add 3000, AX. This is allowed. So whatever the data in 3000 will be added with AX and the result will be moved. Okay, the result will be moved to this same location. This is allowed, but when you just go with the this case, this is not at all allowed. You don't have two memory operand. I mean, with respect to instruction, none of the instruction set architecture won't support this kind of things. Okay. And this currently I don't want to touch, but it's just like as I told you, when you just go with the MIPS architecture, you have 32 general purpose registers. So you have like R02, R31, and similarly, right, you have 32 floating point registers. So F02, F31. Okay, so separate registers. One is for general purpose, another one is for floating point registers with respect to MIPS architectures. Okay, so these things let it be. We will discuss this when you just go much deeper. The next important thing that have been associated with the first one is the classes of ISA. Okay, two things. One is what load store architecture, another one is register memory architecture. The next one is memory addressing. So, what do you mean by memory addressing here? So, we will take this example. Suppose this is memory. If you take when you any memory chip representations, assume something this is a RAM memory. So normally, right, it will be like this 512 KB. For example, I'm writing okay, 512 KB into 8. So what is 512 KB and what is this 8? Any memory, if you take any memory chip, it will be like this 512 KB into 8 or something, let it be 1 MB into 16. So, what this number says and what this number says,
First represent storage and second represent quantity.
second represent? Yeah,
Quantity.
yeah. See, it isn't, yeah, right. So when you take, where is my mouse? Okay, when you take this, okay, let it be. So this is the RAM. So here, right, 0, it till goes, let it be as 511. Okay, address I given. So this what? This says how many bytes it can store. So when it is as 8, it says that it is going to store 8-bit data, which is equivalent to what? 1 byte data. So this number saying this. If suppose if you have 1 MB, so right, again another 8. So the 0th address is going to store a 16-bit data. So this is what the memory thing is going to say. Normally, right, when you just go with any cases, all the processor, it may be either a CISC or a RISC machine, it is going to use a byte addressing to access the memory operand. So clearly byte addressing means what? So this what? So not this part, okay? Every address is capable to address a single byte. So zeroth address is for this, first address, second, 3, 4, so on, so right. So every address is capable to address a single byte. Now, there is a major difference between ARM and 8086. So we need to be a little bit careful because something when you just go with the ARM, it should be purely memory aligned. So what is memory aligned is since all the registers, whatever we are going to use, say suppose, okay, let it be. I'm just taking a 4 byte. So I mean, for example, as per writing, I have an character, I have an integer. So integer is 2 bytes. Just for example, I'm writing. So this is going to be 1 byte. So what is happened here is, since okay, this is the 0th address, this is the first address, this is second address, and this is the third address. So okay, let it be A will be stored. Since it is a character, A will be stored here. Next integer 2 byte, right? Since it is 2 byte, maybe right, it won't take 1 and 2. Instead, right, it will be here. So B will be stored here. So this is what I'm saying. So when you just go with the memory, I mean, in case of ARM, it is completely a memory aligned. So the bytes, whatever we are going to access, the address, what we are going to take, right, that should be mod of that. So say for example, the address mod bytes, it should be always 0. So in case of ARM, it should be purely a memory aligned, but this is not in case of Intel. So just when you go for the Intel or a CISC based machines, if you take a CISC based machine, the same thing is allowed. So it may take a and 0 byte, it will be there, and the first byte and second byte B will be there. So this will be, I mean, this two will be allocated for B and this will be empty. But it will allow to store, but the common case is, right, it may take some extra cycle. Here it takes extra cycle to fetch the data. But in case of ARM, it won't allow it. So clearly it is a memory aligned case. When you go for ARM, it is completely a memory aligned case. But all those things, all whether it is a ARM, whether it is a RISC or CISC architecture, it is going to use a byte addressing to access the memory operand. But more specifically, if I want to speak, when you go with the ARM, it is purely a memory aligned. Memory aligned in the sense, as I told you, right? So whatever the address divided by the number of bytes, mod the number of bytes, it should be always equal to 0. It should be aligned in such a way. Yeah. So that is about memory addressing. So next one is the addressing modes. When you talk as addressing mode, the way of determining the address of the operand, it is not the address of the, I mean, rather than saying it is the address of the operand, It is to say, right, the way how to specify the operand. Okay, so that we are saying it as addressing mode. So clearly with the previous examples we have discussed. Here, right, what is this this operand and this operand, right? It is going to be a memory, registers, right? So in these instructions, we have used the registers. And when you take this instruction, we have used the memory operand. Okay, so it is all about that. So addressing mode is going to say how to specify the operand for the instructions. Yeah, and there are different types of addressing modes. And this case, right, here majorly three categories has been explained. But again, it is purely depend upon the architecture. You may have more number of addressing modes. But here in this textbooks, they are classified into widely classified into three categories. One is register type, another one is immediate, and the last one is displacement. So we'll take an example. When you just go with the yeah. Here we have an example. When it is an immediate addressing mode, when you talk as immediate is nothing but constant. So why the word is as immediate? Assume that if you give these instructions to execute, so what will happen? This 5 will be appearing in the instruction immediately. Okay, it no need to fetch anywhere from any, memory or nothing. So directly, right, this 5 will be there in the instructions. So immediately it will be there. So that's why, right, next to the operand, the data will be appeared immediately. So that's why, right, whenever you have a constant in the addressing modes, they will refer to as immediate addressing mode. So when it is immediate addressing mode, the operand is a constant within the instruction itself. So here what this instruction does, clearly, right, we have add R2, R0, #5. So these two things will be added and that place the result in R2. And here, so compare R0, #1. But internally what is happening? Subtraction will happen. This and this will be subtracted and accordingly the flags will be affected. We need to make choice. Similarly, right, move R1, 1. So they are moving the data 1 to the R1. So always you remember any cases. So this part, right, source will be there and this part will be the destination operand. Yeah, as we do it in C, right? The same thing we are doing it, right? Okay, so this will be your destination register. So these are all the source registers. Okay, so the first type is immediate. So what is immediate addressing mode? It is nothing but the constant X. The next one is register addressing. So when you take the register addressing, clearly the operand it's a registers. So this just if you check, you get to know, right? So all those things are registers. So it is going to be register addressing mode. The next one is immediate offset. Immediate offset, when it is as offset, okay, just keep remember when it is as offset, it is something we are going to add to the base registers. This have you looked somewhere? Have you come across this in your high level language?
Left shift or right? Left shift or right shift?
No, left shift or right shift. Yeah, no, nothing like that. We are not doing any shift operation.
Content of
Okay, we are. What is happening here? What is the statement they are given? Constant address is added to the registers. Some immediate offset value we are adding to these registers. It is something like this. So first case, right, 4, then #8. Where we have seen this?
In looping statements.
arrays, ma'am.
Huh?
Array.
Yeah, right. This is array. Correct. So what we are doing, the same cases, right? We are giving it as a of 0. What is, so it is something like what? A plus 0, isn't it? So star of a plus 0. So it is, when it is a of 2, right? So it will be what? Star of a plus, like 2 into 4, it is 8. You got it or not? So similar. This is what we are saying it. When whatever the programming high level languages we are writing, for every constructs, not for even for the pointers, for everything, right? We have an equivalent addressing modes will be there, because those are all the things that how to specify the operands. Again, right here also you may get a question like this. So maybe right they may give us C syntax for that. So for that C syntax, you need to write the appropriate addressing mode, or you need to identify the appropriate addressing mode. So this side they may give the constructs. So the programming constructs, and this side they may give the addressing modes, and you need to map what kind of addressing mode will be suitable for what kind of programming constructs in your high level language. What is programming constructs? What is programming construct? Am I audible, guys? I need to check am I alive.
Like how the instructions are processed.
You no, I forgot about assembly language or computer architecture, all those things. I'm generally speaking, what is programming? When you are writing high level languages, or when you are going with high level languages, what the code says. I'm going to kill you all. Actually, like what is the outcome of C and C++ subject? You read C and you read C++, right? What is that? They, being a CC students, you should know all those things. See, programming constructs, as the name implies, so that is something which is essential for developing the code. Constructs means, yeah, construct is nothing but the developing. So something essential for writing the code. Which are all essential for writing the code? System, keyboard, monitor. Am I right?
The
Let it
if
be.
statements, looping statements.
Yeah, of course. Why this much time to say? All the 4 units you read in C and C++, those are all the programming constructs. Start with the variables, data types. Your conditional statement, your looping, your functions, arrays, structures, unions, files. So those are all what programming constructs. So only with the help of those things you are writing the programs. Based upon the logic, which programming constructs you are going to use is purely depends on you. That's what, right? Even when I'm going to take first years, right, I keep insisting that if any culprit from my class is there in C, I mean, some C students may be here. Is anybody is there? I, I remember for these people, I handled C programming. I keep insisting and I'm just saying it because when people asking for give more programs, so by giving more programs to you, it won't make you practicing with the programs. So we are there to make you clear with the programming constructs. So for what kind of application, what kind of programming constructs you need to apply, the syntax, the purpose. So only those things we will explain. The programming practice only by yourself it will come. Like that I used to say also. Okay, so what is that programming construct? So at least hereafter keep remember this. Like whatever the things that are essential, which is nothing but your data type variables, CF conditional statements. I mean, you are looping pointers, structures, unions, arrays, functions, whatever it is. Okay, so those are all the programming constructs. So definitely right. Whoever is going to set the question paper, I'm going to give 2 questions based on this. I don't know what questions I'm going to give, but I'm going to give it out. I said what is that question, what the question is going to be. So this side, right, I'm going to give an addressing mode, and that side I'm going to give a programming constructs. So you should be thorough with this. Addressing modes you read in CO. Have you read or not?
Yes, ma'am.
Yeah, you read. Okay. So be thorough with that. I may give you anything, you need to map it out. I'm going to give it. Damn sure I'm going to give it. Okay. So this is the immediate option. The next one is PC relative addressing. So when it is a PC relative addressing, it is purely associated with the branch instructions. So hope you know about the branch instructions. Suppose I'm writing a code. So add of something. After adding it, so I'm just comparing whether or not is equivalent to #2. So when it is equivalent to #2, I'm writing branch equal. I'm asking you to go to some address. Okay, so these are all in some address like electric 2000, so 1004, 1008. So after comparing it, so if it is equal, it is going to some address 2000 and it will address it. Okay, so whatever the program counter, this is the program counter. You know what is program counter. So whatever the instruction that is executing currently, address of that will be stored in the program counter. So it will be added to this and it will move to that location and it will start executing the instructions. Okay, so that they are saying it as PC relative addressing. PC here is what? What is PC here?
Program counter.
Counter. Okay, it is not a personal computer, it is a program counter. So band address, so whatever is the sum of the PC and a constant in the instructions. So this was the same example. Okay, when you are comparing, okay, equal, sorry. So branch equal, it will go to this address. Clear. So these are the like a major addressing modes they have explained. I'm not sure, is there any other address, because you have plenty of addressing modes. Have they mentioned any other addressing mode in your CO? Or only these 4 things?
No, ma'am. We have more.
Only these 4?
12 addressing
More.
modes.
Yeah.
12, ma'am. 12.
Very good. Then only right, it will be good for me to select a question. So be thorough with that. What is that addressing modes and what are all the different ways to specify the programming constructs? Because say, okay, this you have clearly understood. This is going to be a single dimensional. I may give 2 dimensional. For 2 dimensional, what type of addressing mode you need to use? For pointers, what type of addressing mode you need to use? So those things and all you need to be thorough. You just try to map it. Okay. The same things. Again, whatever the examples I have given, the same examples. It is ARM addressing modes. Some of the 2 registers. So where 1 register is multiplied by the size of the operand in the byte. So, auto increment and auto decrement addressing is there. We'll see. But when you just come into the lab, right, there are few instructions which automatically does that. Once you fetch the instructions from the data, automatically it will be incremented. So we can sometimes we may need or we may not need it. Okay, so those things can be done with the help with respect to ARM instruction set. So the next important thing is the types and size of the operand. So when you just go with the size, so the size may vary. Again, it may vary to any case. It may be a 8-bit data. It may be 8-bit data, 16 or 32 or 64-bit data. Or else in case of floating point operation, it may be a 32-bit or a 64-bit. So various operand sizes are allowed with respect to any of the architectures. So you may have a doubt how it is differentiating. This one, say, if suppose if I'm doing with this LDR or not comma some address. So this one clearly it should be a 32-bit address. What to say? 8-bit. The address should be like 8-bit. It will be. I think you have come across like this. Am I? Have you did like this or not? Okay, 32-bit addressing means this is the hexadecimal value. You know about hexadecimal. So 1 bit in hexadecimal is equivalent to 4 bits in byte. Is 1000. If it is 0, it is 000. Got it? Okay. So what this instruction is, it is just loading the data when the address, let it be. So say for example, I am just given as 1000. Okay. It is trying to load the data from 1000 to R0. So which means what it does is, so we have like 1000, 1001, 1002, 1003. So here, right, it will going to take 4 bytes. It will fetch 4 byte and it will move on to the register R0 because R0 is a 32-bit registers. So it will collect 4 byte data, 4 bytes from the memory and it will go. Suppose if you, this is for what, 32-bit. Okay, 32-bit, if you want to load, you can load 32-bit. Suppose if you want to load 16-bit. So you have a separate instruction for this, LDRH R0, 1000. So what this instruction does, it will take the data from this. So LDR H is like half word. So it will take the data from R0, this and this, and it will put the to this one, R0 registers. Okay, so this case, right, it is going to be 32-bit, and this case, right, it is going to be what is that? It is going to be 16-bit. But keep remember, it should be after this, if I'm trying to do this, okay, add R0, R1, okay, R0. Now, what the size of this? What the size of this? After executing this instruction. So I'm giving like this, LDRH R0, 1000. So since I used half, how many bytes it will load?
2.
2 bytes, right? Since it is LDRH, it is going to load 2 bytes. Below this, I am given an instruction like this, R0, you know all the register size are what? All the
4
register
bytes.
now what? 4 bytes. Okay. But we have loaded only 2 byte data into that. Now my question is, this instruction is going to work with the 16-bit data or a 32-bit data?
$32.
32.
32. But we are given only 16-bit. What will happen to the remaining 16-bit?
Zeros before that.
Yeah, right. Automatically, what will happen? It will be 0 extended. If suppose if you read the architecture of ARM, there is a one component called a 0 extended component will be there. So automatically, right, it will be extended because all those things are 32-bit instructions. Clearly, all the operand is of 32 byte. So, 4 byte only. Okay. If suppose if I want to need 8-bit, what is that instruction? It is what it does. LDRB R0 B. So it is byte R0, 1000. Okay. So now write this. It will load only whatever the data in this case. Whatever the data in 1000 will be loaded into this, and the remaining 3 bytes will be 0 extended. So which means, right, we have like a variety of operand sizes. It may be 8, 16, 32, or 64, and even for floating point operations, we have 32 and 64 bit. Clear? And next one with respect to instruction set is the operations. So what are all the basic operations that it can be done? This one. So when you take any instruction set, they will be broadly classified into these categories: data transfer instruction, arithmetic instruction, logical instructions, control instructions, and the floating point operations. So data transfer, you know, right? Suppose this one, right? Move A, B, or LDR. Sorry, not this one. Move R0, R1. So LDR, R0, some address. So this one. moving the data between registers and the memory, or between the registers and the floating point or special registers. So whenever, right, you are transferring the data from between any two things, then it is going to be a data transfer instructions. So arithmetic and logical instructions, you know, right? Arithmetic instructions, add, sub, mul, those are all the arithmetic instructions. Moving on to logical instructions. So this one, right? You have an AND instruction or XOR. So those comes under the logical instructions. And the control instructions. Moving to control instructions, the control branches and the jump you have. And again, right here also, when you talk about the control instructions, you may have something like a conditional and unconditional jumps. Control means, hope you know, control transfer means, so from somewhere it is going to execute some other line. So when it is go for some other line, it may be purely depends upon some conditions, or it may not be a condition. So say for example, I'm giving like this branch equal. So clearly what it is a condition. Only the above instruction, when something is equal, then only, right, the condition will goes. But when you just go with the condition here, right, I'm just adding two things, add R0, comma R1, and then I'm just giving jump. Is there any relationship between this and this? Between these two instructions?
No, ma'am.
No, right? So this is what? It is unconditional. Unconditionally we are transferring the control, but this case conditionally just we are transferring the control. So that's it. When you just go with the control transfer instructions, it may be either conditional or unconditional cases. It is not only with respect to branches and jumps. Other than that, we have one more case. What is this? Subroutines. What is subroutines? What is subroutines?
Procedures. Function.
Functions, right?
Yes.
In your programs, I mean, we have this right main. So inside this we have a function called add. Okay, so this function has to get added. You have an instruction, right, call. So even when you have an instruction like calls, automatically, right, it will move to that location. So call 6000. So it will go to the location. So this 6000 will contain a function for add. Similarly, ret, this is also a conditional control transfer instructions. After executing the function, the raw statement should be a return. Then only, right, it will transfer the control to the main programs. Okay. So these things will come under the control transfer instruction. And you have floating point operations. Some floating point instructions is there. And check out these things. Okay. So data point stack pointer, I will explain like what this is exactly tomorrow. Okay. So you have a floating point instruction also. Okay. So majorly, right, when you just take any architecture, you will have an instruction set, and those instructions will be fall into any one of the categories. So preferably it will be into data transfer, arithmetic, logical, control, and the floating point unit. And this is an example of your MIPS architecture, because as you are going to use all the instructions for the rest of the cases, at least you need to be thorough with few instructions. Not all the instructions, at least you have to be, know about all those instructions. This one, right? This is data transfer, I told you. So most of the cases, it will be load instructions or move instructions. When you go with the arithmetic, all the additional instructions and the logical instructions, and or shift, those comes under logical instructions. Control instructions. So this what? Branch. These are all the conditional instructions you have, and these are all the jump instructions. ERET, I told you ret, right? And here, right, in case of MIPS, it is ERET. And this is from exceptions. And for the normal functions, I think ret is the case. And this is the floating point instructions. Anyhow, right, we are going to use all those instructions in our examples. When I'm just going to explain about some parallelisms examples, you will see all those instructions. And And again, I'm repeating, like this is just for example aspects, we are going to use it. Nothing to memorize. Just keep remember. But for lab aspects, you should know about the instruction set of ARM. Then only right you can able to write a program. But this case, just knowing the MIPS instruction set is enough. I mean, here it is there in described manner. So when you just go with the control flow instructions, here write this what I said. You have a conditional, unconditional, procedure calls, and returns. I just now explained, right? When you just go with the control flow instructions, two types, conditional and unconditional. Even procedure calls. Procedure call is CAL, jump, unconditional is jump, conditional is branch equal, and return is RET. Okay, so all those three, all conditional, unconditional procedure, all will use PC relative addressing. Just now we are seeing, right? So branch equal, so 2000. So this is R call 6000, R jump 4000. Okay, so this correct. So these are all comes under control flow instructions. Clear? And when you take the control flow instructions, this is very important. Again, you may get a 2 marks based on this. Control branches test the content of the registers. So this is very important, which means, see, if I'm comparing this, okay, let it be compare R0, R1. And I'm giving branch equal, moving to the location. For this case, I'm saying. So what this branch equal does is, it will check the content of the registers. Okay, this is in case of MIPS. But in case of 8086 and ARM cases, the same thing. Suppose if you have a compare R0, okay, assume that in this case, this is ARM. Okay, consider this as a MIPS. Okay, in case of ARM, if I give like this branch equal 6000, here what this equal check is, it will go to the flag registers. So you have a flag registers. In that, it will check the zero flag. If this is set as 1, if the zero flag is set as 1, this condition will execute. Clear? So that's the difference between MIPS and with the 8086 and ARM architecture. So keep remember, when you go with the MIPS, the conditional branches will test the content of the registers. So it will test only the content of the registers. But in case of ARM and 8086, it will test the condition code bit. So the condition code bit is this one, equal. So here when it is equal, whatever it is, and it is equal, it will check the flag registers. Okay, all your condition codes are associated with the flag registers bits. So keep remember. Okay, and the other difference is ARM and MIPS will place the return address in a register, which means I will write it here. If suppose you are writing an instruction like this 6000, 6001, 6002. Here I am just call this function, call the something at 8000. So here right it will goes to 8000 and it will execute. So this is the function. So assume this is your main program. After 6000, okay, let it be 6003. Every function, when it is a function, right, it has to be end with a return statement. Okay, so now, right, what the ARM and MIPS doing is, when this instruction is going to execute, the control is going to transfer here. When the control is transferred, after executing all those, it has to return to the address 6003. Okay, it has to return to the address 6003. So how do we know that it has to return to 6003? So before calling this, this address has to be stored. So in case of ARM and MIPS, the return address will be stored in registers. So few registers will be dedicated for storing this. Okay, so return address will be stored in the register. But when you go with the CISC or Intel machine, the return address will be stored in the stack. Here, the stack here, what we mention is memory. Got it? So this is what they are saying. ARM and MIPS procedure call places the return address in the register. But in case of 8086 or this what Intel, okay, it places the return address in the stack of the memory. So these are the few differences with respect to control flow instruction with 8086 and MIPS and ARM architecture. Okay, so keep remember this part. This is very important part. I think I will continue this in tomorrow's class. So till this, I make a short recap. So this today's class we have been more on to designing a computer architecture. So when you are going for designing a computer architecture, instruction set plays a vital role. So because that is going to act as a boundary between the software and the hardware. And when you just in instruction set architecture, what are all the things that has to be considered is first one is the classes of ISA. Two categories we have: load store architecture and register memory architecture. Next, the memory addressing. So purely it is going to be a byte addressing. So for all the architecture, it is going to be byte addressing. But when you go with the ARM, it is completely memory aligned, and that is not possible in case of Intel. And the addressing modes, I told you, you need to map the what are all the programming constructs that are available in high-level languages and which addressing mode may be suitable for that programming constructs. So you need to be thorough of yourselves. The next one is the operand size, what we are going to mention in that registers. It may be a 8, 16, 32 or a 64 bit. Next, what operation the instruction is going to perform. So majorly they are classifying into data transfer, arithmetic, logical, control and the floating point. So I have explained like what is data transfer, what is arithmetic, what is control. And when you just go with the control transfer instructions, there is a few difference between ARM, MIPS and the Intel. So this I just given with an example. Okay. So with that we will conclude today, and tomorrow, right, I will go with this encoding and ISA and the summary part of this. Okay. Till this, if you have any doubt, you can ask me.